Hello, this is Brian Washburn. I'd like to talk about the concept of mechanical energy. Okay. Before I like to do that, I'd like to review the concepts of work and kinetic energy. So we can define a scalar function called work, which is equal to, so that my notation I'm going to use is work. And when I calculate work, I have to choose a path. So I have to have a starting point and have to have a stopping point. So if you take a look at my figure here, 1 is the starting point, 2 is the stopping point. And then I have a position vector associated with every point. So this notation says I start, this is the position vector for starting point, it's the stop point. I go from 1 to 2. And that path might be something simple, it might be complicated. So again, I start from 1 and I might go around and go back to 2. So that might be a possible path. And then this is f dot dr. This is a path integral from 1 to 2. Okay. And then in order to do that, I have to take a dot product of my force. In this case, it would be a two-dimensional force, and dr would be a little vector r in the xy plane. So this is my definition of work. Kinetic energy is the energy associated with motion, and I define kinetic energy as 1/2 mv squared, where v is really the speed. So again, this is a scalar quantity, and both work and kinetic energy measured in joules. Okay. Now, what I can say is I can have a theorem between the two, and then what does work do? Work changes the kinetic energy. So the work done, okay, from 1 to 2 causes a change in the kinetic energy of a system. Okay. Now that is the work kinetic energy theorem, and we'll show this in class. And you derive this in engineering physics 1. So there's a couple. This is a very powerful theorem because what happens is this is the work done by any kind of force. The force could be anything. It could be gravity, it could be friction, whatever. There's no requirements on what the force is, and I can always, given a force, I always can calculate the work, and that causes a change in the kinetic energy of a system. Okay. Now, you may remember from engineering physics 1 the concept of a potential energy. Okay. But potential energies can be defined for what's called a conservative force. And so let's talk a little bit about conservative forces, okay, because these are very special forces. And a good example of a conservative force would be gravity. Gravity is a good example. There has to be two conditions. Not all forces are conservative. An example of a non-conservative force would be like the force of friction, force of air resistance. Okay, there are two conditions necessary for a conservative force. Now, again, why are we interested in conservative forces? Well, if we have a conservative force, if a force is conservative, we can define a potential energy associated with that conservative force. Okay, but first we have to show that the force is conservative. Then we can define or write a potential energy associated with that. What are the conditions for a conservative force? First of all, that the force must be only a function of position in space. Okay. It cannot be a function of time or velocity. Okay. All right. Cannot be a function of time or velocity. Why is that? Well, if it's a function of time, that means the total energy, in the end, the total energy of the system will either increase or decrease with time. Obviously, that energy is not conservative if that's the case. Okay. So the force can only be a function of position, and gravity is a force only a function of position. So that's a good. So gravity satisfies the first condition. Okay. The second condition is what I would call the force must be path independent. Okay. What does that mean? Well, there's two ways we can define that. It means that the work done, so if I have any 2 points in space, okay, here's 1 and here's 2. The work done going from, say, a path like this and a path like, say, like this is the same. Okay, so the work done is independent of the path. Okay, and so what we can write that in terms of mathematical we can say that the work from 1 to 2, okay, is is independent of any path I choose. All right. Now, what that also means is that if I take a path and go from 1 and make a closed path, okay, that the work done, that also means that the work done for any closed path is 0. Okay, because I start off and stop at the same place. Okay. Now, if we want to write this, now let's write this idea, work done by a closed path, in a more mathematical language. Okay, what we can say is that, well, the work done in an open path, we can say it looks like this. This is again a path integral. We can write down the work done for a closed path in using again an integral. But the way I would write that is the work done in a closed path looks like a path integral with a closed over some. So I have some closed path of C, and I use this circle, the integral of a circle, to represent a closed path. This is my integral over a closed path. Okay, and that's equal to 0 if I have a conservative force. Okay, that's the first. That is, so the condition is path independence, and so there's two ways to show. Well, so we actually, what we can show is that something is path independent. That I can show that the work done from 1 to 2 given any path is always equal to the same value. Okay. Now there's another condition. The other condition is, and in fact this is actually a more practical condition. Instead of looking at the work done, I can show that, well, I can show that the curl of the force is equal to 0. Okay, so that's another way of showing that a force is conservative. Okay, so this is again, this path independence depends on the curl of the field. So if the curl is equal to 0, then it is also a conservative force. Now this guy here, this curl and this integral here, they're related to each other. And they're related to each other by what's called the Stokes Theorem. And what the Stokes Theorem says, say I have a vector field f, so this integral here, I said this is a path integral about a closed path, but really it has a better name. This is called the circulation. Okay. And this guy here is called the curl. Okay. And so what the Stokes Theorem says, writing the Stokes Theorem, says that the circulation of a vector field, this is from Calc 3, is equal to, I have to do an area integral over an area of the curl of the vector field dot some area surface here. That's Stokes Theorem. This is called the Stokes Theorem. All right. But if the left-hand side is equal to 0, then either dA is equal to 0 or the curl is equal to 0. Okay, well, obviously, if I have a real surface, dA is not equal to 0. So that means this thing here is equal to 0. So, again, conservative forces only depend on position and they're path independent. And you can show that they're path independent two ways. You calculate the work done for two paths, show they're the same, or you show that the curl of the force field is equal to 0. And this curl is going to be a much more practical way of doing it. Okay. Now, given what we can do now is, since we have a potential, since we have a conservative force, we can define a potential associated with it. So the way I'm going to define my potential, the potential energy is going to be equal to minus the work done from some reference point to some point in space. Okay, and that's going to be equal to minus the integral of, well, I'm going to start off some reference point to some point in space of f of r dot dr. Okay, now you may say, why do we have this minus sign there? Okay, well, the reason why we have the minus is because what we, in the end, we want to define is the total mechanical energy. And the total mechanical energy is equal to the sum of the potential energy plus the kinetic energy. So I can define the total mechanical energy as T plus U. Okay, and what we're going to show is that for a system where there's no non-conservative forces, or there's only conservative forces, the mechanical energy of the system is conserved. Okay. And then how are we going to show conservation of a mechanical energy? The way we're going to show it is that, well, from the work kinetic energy theorem, the change in kinetic energy is equal to the work done, okay, from 1 to 2. Okay. However, the work done by 1 to 2, and for a conservative force only, is equal to minus the change in its kinetic potential energy. That must mean that, well, these two are equal to each other, so delta T is equal to minus delta U, or I can say that delta of T plus U, I want the plus sign, is equal to 0. That means that the rate of change of this quantity here, which is the total mechanical energy, is equal to 0. That must mean T plus U is equal to some constant over time. So that is conservation of mechanical energy. Okay, as long as there's no non-conservative forces acting on the system, there's only conservative forces, then the mechanical energy of the system will be conserved. Okay? Okay, now there's one more thing we want to talk about. So if I give you a force, I can calculate the potential energy. What happens if I give you a potential energy? Can you get the force? Okay. Well, what we can show, remember my integral U is equal to minus the work done, which is equal to minus f in one dimension, say f dot dx. Okay. If I take a differential on both sides, I can see that du is equal to minus f. We should probably put an x there. F of x dx. So that I can say that du dx is equal to minus fx. So if I know u, I can just take the derivative of this in order to get the x component of the force. Now forces are three-dimensional things, so we have to write this. This is only for one dimension. So what we want to do is we want to write this in the context of a three-dimensional vector, a three-dimensional derivative or vector, or more specifically the gradient. Okay, so if I define the term grad or gradient, and let's just do this in Cartesian coordinate systems. So, and eventually we're going to do it in any coordinate system we want. So I'm going to define a Cartesian coordinate system like this. Now this thing here is really a vector operator. Okay, why is it that? First of all, it is a vector, so it needs the arrow because of x hat, y hat, z hat. Okay, and the reason why we say it's an operator is because it has these derivatives. It operates on a function. By itself, it doesn't do anything. It has to operate on something. Now what I'm going to do is I'm going to use my own little notation. Now, why do I have partial derivatives? Well, my force may be a function of x, y, and z, and so I have to use partial derivatives in order to get those. So the way I'm going to use a little simpler notation. Partial x is represented by this symbol here, partial y by this symbol, and partial z by that symbol there. Okay, and then I can rewrite all three derivatives in a nice format, saying that the force, the force is going to be minus the gradient of the potential, and this is a very important result. Now, in terms of vector calculus, remember the force is a vector field. The potential is a scalar field, and this operation of a gradient onto a scalar field gives me a vector field. Okay, so that's how I can get the vector field, the force field, from a potential field, a scalar field. Okay, so that's the summary of what we're going to do in class. Okay, again, what we've done is we define the concept of work. Work is a scalar quantity. Again, this is a path integral. Okay, dl. Your book writes dr. I like writing dl, but I think you understand what's going on. This is a path integral from 1 to 2. That is the work done. Kinetic energy is the energy associated with motion. Okay, and then the work kinetic energy says that the work done by any kind of force changes kinetic energy. We define a conservative force. Conservative force is a force that only depends on position, does not depend on time and velocity, and it's path independent, meaning the work done from one point to the other independent of the path I choose to get there. That also implies that if I take a closed path, the total work is equal to 0, and that that relationship gives us a nice way to calculate a conserved force using the Stokes theorem, or more specifically that the curl of the vector field, the curl of the conserved force is equal to 0. All right. And then we define the concept of mechanical energy as the sum of potential plus kinetic energy. What is potential energy? Potential energy is the energy stored in a vector field. That's a sophisticated way of thinking about it. I can only have a conservative force to do that. I can store, now since you've had EP2, you can think about fields. Okay, you didn't talk about that language in EP1, but one thing you can do in a field is store energy in it, and U is the energy I store in the gravitational field, and is conserved. So for a mechanical system, mechanical energy is only conserved if there's no non-conservative forces acting on it. We then, given the potential energy, I can calculate the force by taking the gradient of that. Okay. Now, one thing we're going to do in class is we're going to try to do this exercise. So one thing I would like to show in class, or have you work on, is that consider I have gravity, okay, mg, downward, okay, the force of gravity. Show that the work done by gravity for a closed path of a circle. Did I spell circle wrong? Well, probably. Anyhow, yeah, I definitely spelled circle wrong. Sorry about that. But anyhow, so what I want to show is, say I have some xy component system. I have a circle. I take a circular path. I have the force of gravity acting downward like this. This is x, this is y. Show that the work done for the circle, there I spelled it right, equals 0. Okay, so we'll see you in class. Take care. Bye-bye.